Hello students, so welcome back to the channel. So in this video we're going to be continuing our organic synthesis revision, and this video we're going to be handling specifically phenol together with the revision of carbonyl compounds. Now like we said, we are going to be repeating the same procedure. We look at how we can prepare either of the compounds we are going to revise. We look at how the reactions, how each of them is going to be reacting with the different organic compounds, and later we look at the revision assessments for which we can apply our revision. Now the video is presented to by Olgan Yusuf. Make sure that you like the video, subscribe to the channel, and then share the video to your colleagues. For any inquiries, please use the YouTube comment section platform. You'll be answered as quickly as possible. Now looking at phenol, if we start from the preparation, we are going to first prepare it from the Chimneys process. Now I highlighted this reaction as the first reaction simply because a lot of mock bodies like assessing it. So if you're having your benzene ring attached to an R group, but this R group, it must be a tertiary R group or a secondary R group. So if you're having a compound of a compound of this nature attached to the benzene ring, we simply get our oxygen and then we heat in a sealed tube, and then we get a carboxylic acid of this format. Now to remove all this chain, to remove the propanone, to remove the propanone group, we simply get an acid and then we react it with our compound so that we can get both phenol and propanone simultaneously. Now you can proceed by saying that also the chimney is going to be produced by reacting benzene with propene in the presence of phosphoric acid at a temperature of 250 degrees Celsius and 30 atmospheres. Now what you should note here is that whenever you're using phosphoric acid, temperature has to be specified together with the other conditions. So for us to prepare chimney, instead of using this reaction, or instead of using halogen carriers to get this compound, we can use another procedure by using sulfuric acid. Now notice that we can get this compound, the chimney. We can get chimney simply by using an halogen carrier together with an alloalkane, which is the previous lesson we had about organic synthesis. But we can also use phosphoric acid, but we say that whenever you're using phosphoric acid, you make sure that the conditions of temperature and pressure are always specified. So for this case, we need a temperature of 250 degrees Celsius together with a pressure of 30 atmospheres to get our chimney. Now make sure that whenever you're writing organic synthesis, we say that reagents which engage in the reaction must be above the arrow, and then the components that do not engage in the reaction, which we call conditions, are always below or down the arrow. Now some of the reactions we have already looked at them under halobenzene, like this reaction. So when you're dealing with the previous lesson, you say that you can easily prepare phenol from halobenzene, and you say that whenever you're using sodium hydroxide, always specify the state. So for us to get sodium phenoxide from chlorobenzene, we have to treat with sodium hydroxide, but it must be under strict conditions, simply because the bond between carbon and chlorine is very strong. So to do that, we need sodium hydroxide at either 350 degrees Celsius or at 360 degrees Celsius. So you pick one temperature. So for this, we went with 350 degrees Celsius at a pressure of 150 atmospheres. So this is going to give us our sodium phenoxide. Now to convert sodium phenoxide to phenol, we use acidified water. Now we see that there are three ways of writing acidified water. One can say dilute HCl, or to prevent mixing words with symbols, you can write HCl and then you put a subscript of aqueous to be its state, or simply you can write hydroxonium ion. Or if you're writing acidified water, you write the water molecule first and then you stroke it with the acid molecule. So that's another way to write acidified water. And once we react our acidified water or our hydroxonium ion or our dilute hydrochloric acid with this sodium phenoxide, we are going to come straight away to phenol. Now remember, we said that what is going to determine the way you are going to be marked in the organic chemistry numbers is going to be the arrangement that you present in your work. So going to part C, you can also prepare it from benzene sulfonic acid, and that is done by fusing it with sodium hydroxide. Now for this case, when you are fusing, we use sodium hydroxide which is in solid state. And that's why I told you that whenever you're using sodium hydroxide, you make sure that you already specify its state. So we get benzene sulfonic acid and then we fuse it with sodium hydroxide in solid state to get sodium phenoxide. And then we repeat the reaction which we have described above to get our phenol. Now you can also prepare phenol from benzene diazonium salt. So if you take a look at benzene diazonium salt, we can simply just warm it with acidified water so that we can get phenol. Now remember, I've already talked about this reaction in the previous video about benzene together with halobenzene. So if you're having a benzenium salt or a diazonium salt, we simply get acidified water. Like I said, you can write acidified water in two ways. Someone else can write H2O stoked with acid and then you warm. The main condition here is that this reaction must proceed after warming, not heating. So you get your diazonium salt, you react it with your acidified water or hydroxonium ion, and then you're going to prepare our phenol. So that's some of the reactions from which phenol is going to be prepared. Now let's look at the reactions in which phenol is going to be participating. Now we saw that in the previous video, we said that any compound containing the OH group can easily react with the sodium metal, and when they do so, the sodium metal simply replaces the hydrogen atom to give us hydrogen gas. So the same applies with phenol. So phenol reacts with the sodium metal to form sodium phenoxide together with hydrogen gas. The sodium replaces the hydrogen atom so that you can get our phenoxide or sodium phenoxide, and then this hydrogen atom that has been replaced gives us a effervescence of a colorless gas which is going to be hydrogen gas. This is a very common reaction in paper 1 of chemistry. So if you proceed and you go to the reaction of sodium hydroxide, phenol reacts with sodium hydroxide in the same way like sodium metal. So simply, also here the hydrogen, for this case the hydrogen ion that is replaced comes and joins the hydroxyl to give us the water molecule. And then later, the sodium ion that has been left joins to the phenoxide to form our sodium phenoxide. So you can proceed with your sodium phenoxide and finding other products such as the benzene ring or phenol. Now you can also react our phenol with silver alkanoids or what you can call silver esters. So let's look at the reaction for that. And that is done in presence of an alkaline medium, and for alkaline medium we are going to be mainly using sodium hydroxide. Now this is going to be a very rare case reaction, and if it's examined, it's going to be in paper 1 chemistry where you have to complete the reaction. So what happens is that this carboxylate group comes and replaces the hydroxyl group, and then we form an hydroxonium ion, and this hydroxonium ion becomes part of the medium that is enabling or inducing this reaction, and then we end up with a benzene alkanate of the following format. Now the other common reaction which is very important is going to be reaction of phenol with acid halides. Now this reaction is very important simply because phenol reacts in presence of alkaline medium. Now we need to understand this very clearly. Majority of the reactions of phenol occur in presence of alkaline medium, because it's alkaline medium that induces phenol to engage into reactions, and we explain that in details when you're handling the revision of the notes. when you're handling the notes about phenol, which is also present in the organic playlist. So once we have that, we get our acid halide, and then there is no need of any halogen carrier. You just present your acid halide, and then the condition for that, or the inducer for the reaction, is going to be sodium hydroxide. And whenever you're using sodium hydroxide, ensure that you specify the set of sodium hydroxide that you're using. But mainly we use aqueous unless we are handling fusing reactions. So we also get a benzene alkylate of that format. R represents the alkyl group. We have already mentioned that. So it may either be methyl, ethyl, or propyl. Now proceeding, we go to the reaction with alkyl halides. They also react in the same way just like acid halides. Also for this case, the inducer or the condition for the reaction is going to be sodium hydroxide. And once we do that, we are going to get our phenol in form of esters. So what this does is that this halogen atom, the halogen atom comes and reacts with this hydrogen to give us an acid halide. After that, the R group comes and attaches to the phenoxide to give us an ester of this format. It's a very important reaction because it's very common under organic synthesis questions. So let's also look at the reaction of bromine water with phenol. Now we summarize this reaction because it's very common in organic chemistry practicals. We gave a video about organic chemistry practicals summarizing all that. Now when you react phenol with bromine in the laboratory, when you get bromine water and you add it to your test solution containing phenol, or else you're going to get a white precipitate, and that white precipitate is due to formation of 2, 4, and 6 tribromophenol. So this is going to be a white precipitate that is formed. So for this observation, now this can also be used as an observation or as a reagent in paper 2 under the questions that we examine about organic synthesis proving or confirming confirmatory reagents. So bromine confirms presence of phenol by forming a white precipitate, which is going to be of this format. So this is the equation, and we mainly ask for the equation after writing the observation. So what happens is that all these hydrogen atoms that have been repressed at these points, they react with the other bromide ions that have been left to give us 3 molecules of hydrogen bromide. Now another reaction of phenol. Now notice that majority of the reactions for phenol, the condition for that is going to be sodium hydroxide. So also phenol reacts with the isonium salt under the conditions of sodium hydroxide in its aqueous state to give us benzene diazonium salts. So for this case, we are going to get an orange precipitate, which is going to be of the following format. We looked at this, and this is more evident in organic practicals. But since we are not explaining practicals, what you need is the structure of the compound that is formed. Now remember, we looked at the mechanism of this in the organic notes that we already elaborated. So since we are just making a revision, we are just going to be just making a review about what you have already covered. So proceeding, we can also look at the hydrogenation reactions. For hydrogenation, we say that nickel is part of the reaction. So you get your hydrogen, you stroke it with nickel under conditions of 200 degrees Celsius. So what it does, it removes the pi electrons within our benzene ring, and then we get our cyclohexanol. Now remember, we told you that whenever you are hydrogenating either alkynes and you want to take them to alkanes, or the benzene ring and you want to remove the pi electrons, always make sure that you're using a temperature of 200 degrees Celsius. The 150 degrees is always going to work for aliphatic compounds with a double bond. So let's also look at the reaction of phenol with zinc dust. Remember that you have already explained this in preparation of benzene. So we can easily prepare phenol. Using zinc dust, and then we heat. Now notice that here I didn't mix symbols with words. I only used words throughout. But if you want to use a symbol, then you write zinc. Then the dust is going to be represented by a state, which is going to be S. and then the condition for that, you put it down the arrow, which is going to be heat to attain your benzene ring. Now here are the examples to apply what you have just revised about phenol. So first we are preparing a diazonium chloride. We are getting a diazonium chloride to a cyclohexene. Now to do that, we have to first get our benzene ring from our phenol from diazonium salt, and we do that by getting acidified water. It's not water, it must be acidified water. So H2O stoked with an acid ion, which induces the reaction, and the condition is warm. But instead of warm, since warming is the same as heating, you'll be marked. So from here, since we don't want the benzene pi electrons in the benzene ring, we have to hydrogenate. We write hydrogen stoked with nickel at 200 degrees Celsius to attain our cyclohexanol. Now for us to get cyclohexene, this is an alkene. And we know to get alkenes from alcohols. That's always concentrated sulfuric acid, and then you heat. But here we say that whenever you're using concentrated sulfuric acid, we have to specify the temperature. So for this case, instead of heat, you simply write 180 degrees Celsius, and then we get our desired product. So you're going to repeat for the same procedure because you have already looked at all of this to get the desired product. Now for this case, instead of the alkaline medium, we have tried the acidified medium so that we can get our carboxylic acid. We have already revised all this. We also looked at all this. So you make sure that you pause the video and then we take that down. So this is a continuation for our revision, and then we call that the end for phenol. Now notice that here when I was converting into a diol, I used alkaline manganate 7, and for this case I heated. If I didn't heat, I would have got a diol. So for this case I wanted to get a dioic acid. That's why I applied heat, and you have already explained this in details. So the others, we have already looked at each of them. Now next we are going to look at, or we are going to cover for this lesson, is going to be carbonyl compounds. Carbonyl compounds include both aldehydes together with ketones. Now aldehydes have this structure, and then ketones have a structure of RC attached to another alkyl group. So ketones have two alkyl groups, whereas aldehydes only have one alkyl group. So for us to get aldehydes, we always use mild oxidizing agents, and you can easily prepare them from alcohols, which is about the previous video we saw that. So mainly we use dichromate, acidified dichromate 7, and then we heat, and then we get the respective aldehydes. Now dichromate is only a strong oxidizing agent in excess conditions, but in limited conditions it can easily give us aldehydes. We can also use copper in oxygen and then a condition of 300 degrees Celsius to attain our aldehyde. Now let's look at another preparation whereby you can prepare it from calcium salts or carboxylic acids. Now these ones are two reactions, the one that gives us aldehydes and also the one that gives us ketones. So for us to get an aldehyde, we always get calcium methanoate and then we heat it. And this is a very common reaction in paper 1 chemistry, where we tell you to complete this following reaction. So what happens is that we get a calcium carbonate, and after getting a calcium carbonate, the remaining product is going to be methanol, if at all you have heated calcium methanoate. So you get methanol. If you want to finish up this reaction, then you add calcium carbonate, and the reaction will be self-balanced. Now another reaction that is going to yield us aldehydes is going to be when you are heating a calcium salt of a carboxylic acid with an unspecified chain, whereby R can represent a methyl group, an ethyl group, or a propyl group. And to do that, we need calcium methanoate and then you heat. And what it simply does is going to give us an aldehyde with the R group that is attached to the carboxylic acid of the calcium salt you're trying to heat. Now another common reaction, now this is a very uncommon reaction and I would advise don't to read it for marks purposes, but your neighbor is rarely going to set this. So you're going to first ignore that for a moment, simply because majority of the students, you mess up with the arrangement of this reaction and then you tend to lose marks. Remember, arrangement is very crucial for a reaction to take place. So if at all you rearrange the conditions of the reaction, you are most likely to get everything wrong. So rather, instead of this reaction, let's opt for the reaction of hydration of alkynes. Now you've already revised this in the first video, and then you see that this is a two-step reaction. So first, it's an hydration reaction. So we have to write water first, simply because it's an hydration reaction. So water struck with sulfuric acid, and then the catalyst or the condition, the catalyst is going to be silver sulfate, and then we stroke it with a condition which is going to be 60 degrees Celsius. And that's what we call hydration of alkynes. And for this case, we are going to prepare aldehydes, which is going to be ethanol. However, if you're having an alkyne with more than 2 carbon atoms, then the resulting compound is going to be a ketone. It's only ethane that gives us aldehydes with this hydration reaction. But note the arrangement for this reaction. It's an hydration reaction, so we write water first, followed by sulfuric acid, and then the catalyst, we put it down the arrow to be silver sulfate, and then stroke it with a condition of 60 degrees Celsius as the temperature. And you have said that it's only ethane that gives us an aldehyde. Other alkynes are going to give us ketones. Now let's look at the preparation of ketones, just like we have looked at the preparation of the corresponding aldehydes. So ketones are mainly prepared from oxidation of secondary alcohols. So let's look at the reaction for that. Now the reaction for preparation of ketones is very common in organic synthesis or organic practicals, whereby we give you a compound and then we tell you to react it with any oxidizing agent. Because any oxidizing agent, the moment it reacts with a secondary alcohol, whereas get a ketone. So if you're having a secondary alcohol and then react it with an oxidizing agent, either dichromate, either acidified dichromate 6 or manganate 7 in acidified medium or any other oxidizing agent, we are always going to get a ketone. So secondary alcohols, after getting oxidized, they give us ketones. Now we also talked about this in the previous session, but said that you're going to ignore that due to misrearrangement of these conditions, which lead to loss of marks. So you're going to go straight away to part G, which I've already emphasized, hydration of alkynes. So we say that if you're having more than 2 carbon atoms, you're always going to be preparing ketones rather than aldehydes. It's only ethane that gives us an aldehyde for this kind of reaction. And you have said that since it's a hydration reaction, water comes first, stroked with sulfuric acid, then later mercury sulfate stroked with 60 degrees Celsius to get the desired product. Now another reaction that is going to give us a ketone is going to be acylation reactions. We looked at this in the previous lesson and we said that this condition must be stroked above the arrow with the reagent carrier must be stocked with the reagent above the arrow, and there is no condition required for this reaction to take place, except at some condition or under some circumstances we may use 50 degrees Celsius to effect this reaction. But it's optional, you either write it or not. However, sometimes if you don't write it, you may deduct half a mark onto your scores. So from Grignard synthesis, we explain Grignard synthesis in details, so we are going to just look at it in the examples given. We have also looked at this, and I've said that for this one, we are going to form ketones except when, if you look at part J, we are saying that when calcium salts of carboxylic acids are heated, they form ketones, except calcium methanoid, simply because we said in the previous preparation of aldehydes that if at all you are heating a calcium methanoid, you are only going to form ethanol. But if you are heating an increased chain of that, you are going to form a mixture of products, and you are going to form both aldehydes and ketones. So for this case, we can form a ketone because we already looked at this reaction in the previous session, also forming an aldehyde. But an aldehyde for that case is going to be the minor product, and the ketone or the ketone for this case is going to be the major product. So the conditions for that reaction is that you must be heating with calcium methanoids, and the condition must be heating reagents above the arrow and then conditions down the arrow. Now another reaction that you can look at is going to be the reduction reaction. Now you have already looked at this in the previous session, that's why I don't want to over-explain it. So we say that for this we need only one condition, lithium aluminum tetrahydride in dry ether. So once you do that, one bond on oxygen gets replaced, and then this oxygen gets bonded to an hydrogen atom, and then the other bond gets bonded to another hydrogen atom. So this reaction basically takes us back from a ketone back to a secondary alcohol from which we derived that ketone. So if you want to reverse a ketone back to its secondary alcohol from which it was derived, we simply reduce it by lithium aluminum tetrahydride, and it's the same to both primary and secondary alcohols. You only need lithium aluminum tetrahydride, and then you stroke it with dry ether for the reaction to be considered effective. Now we also have other reactions which involve preparation of alkanes. Now we can prepare alkanes simply by using amalgamated zinc in a condition of concentrated hydrochloric acid. So what happens is that it removes the carbonyl carbon group, and then it replaces it with the CH2 group. So from this reaction, the reagents that we need is amalgamated zinc, which is written as zinc stroked with mercury, and then the inducer for the reaction, we put it down the arrow, which is going to be concentrated hydrochloric acid. So the carbonyl carbon group is removed and replaced with CH2, and then the others remain the way they are in the question or item. Now let's look at another. Now this is basically a repetition of what we already talked about in the previous video. We said that if you're handling aldehydes, if you're removing the magnesium halide, like we said in the previous video, you're going to use acidified water. You can either write hydroxonium ion, or you can write HCl and you put a subscript state of aqueous, or you can say H2O stroked with the acidified condition to get the desired alcohol. So we looked at this in the previous lesson or session. But we say that for ketones, when you're using a ketone, like for example this, if you notice here we have been using aldehydes. But if at all you're using a ketone and you want to increase the number of carbon atoms in your chain, and you want to remove your magnesium halide, when you use the ketone in the first reaction, then the hydrolysis for that reaction is going to be done using ammonium chloride. But you make sure that you give it a state which is aqueous, because there's no hydrolysis reaction that is going to proceed if at all the reagent that you're using is in solid state. So when you're using a ketone, when you have used a ketone in the first place, always use ammonium chloride to remove the magnesium halide, such that you can get your corresponding alcohol. This is very important because this is the shortest reaction in increasing length of the carbon chain in an organic compound. So proceeding, we're also going to look at gamidyl halides being formed from ketones. Now this is a common reaction, and we say that for this reaction, we do not need dry ether. So you simply get your ketone and then you heat it with phosphorus pentachloride. What it does, it removes the oxygen atom, and then we get two chlorine atoms attached to the same carbon atom that carried the oxygen atom. So for this reaction part O, we are going to ignore it completely, because these conditions or these reagents are not available in the laboratory, so we have discouraged both examiners and teachers from setting it. So going to part 2, we are going to look at the reaction with sodium hydrogen sulfide. Now in practicals, or in organic practicals, we use sodium hydrogen sulfide to confirm presence of carbonyl compounds. So both aldehydes and ketones react with hydrogen sulfide to give us a ketone of sodium hydrogen sulfide. I said both aldehydes together with ketones react with sodium hydrogen sulfide to give us the corresponding sodium hydrogen sulfide salt, and this confirms presence of carbonyl compounds in organic practicals. Now the other reaction is going to be the reaction with hydrogen cyanide. Now hydrogen cyanide is very unstable. Though some students use it, we don't reward marks for hydrogen sulfide being used as a reagent on any organic synthesis. Hydrogen sulfide is very volatile, so in the laboratory we just prepare it using reagents or potassium cyanide in dilute sulfuric acid. And this is done at a temperature below that of room temperature, and it must be between 15 to 20 degrees Celsius. So if you're having your ketone and then you want to react it with hydrogen cyanide, we have to first prepare it by reagents or potassium cyanide in dilute sulfuric acid, and then we provide the condition of 20 degrees Celsius to get the corresponding hydroxynitride. Now this reaction is very common in paper 1 chemistry and also in paper 2 of mock bodies, so you may not miss it out. And we looked at this reaction under carbonyl compounds in the notes under the organic chemistry playlist. So you're going to ignore this reaction for preparation of alkanides, and then we'll go straight out to reaction of carbonyl compounds or ketones together with hydrogen or together with hydrazine. Now majority of you don't know what you call hydrazine. Hydrazine has 2 nitrogen atoms attached to 4 hydrogen atoms. So for this hydrazine to react with any aldehyde or any carbonyl compound, the condition must be sulfuric acid. So this acid ion wasn't supposed to be down the arrow, but rather it was supposed to be stroked with hydrazine up the arrow. So as they react, we get our compound, which is going to be of the following format. Now we looked at how we can do this mechanism under the notes, and we say that this mechanism is going to carry over 4.5 to 5.5 marks, depending on the examiner. So you make sure that you can write out its mechanism properly and appropriately, because it's a very common mechanism to be examined. Now other reactions that are going to follow the same path, like hydrazine, they are going to be hydroxyns. So hydroxyns also react in presence of an acid as an inducer. So since it takes place in the mechanism, we shall take this hydrogen ion up. So there is no condition for this reaction. We also looked at the mechanism of obtaining this under carbonyl compounds video. So for part, also this is an hydrazine, but this is attached to a benzene ring. That's why we call it phenylhydrazine. And they react in the same way, just like hydrazine, to give us the corresponding product. And we looked at the mechanism of this reaction specifically. So also in synthesis, this is very essential. Then they also make the same reaction with semi-carbazine. Now, one thing we should note here when you're using a semi-carbazine is that the nitrogen atoms which are close to the carbonyl carbon group do not engage in the mechanism, or they do not donate any of their atoms, but rather the nitrogen atom that donates its atoms, the 2 hydrogen atoms, is going to be the nitrogen atom which is not attached to the carbonyl carbon group. That's very crucial, and you should always remember it, because majority of you mess up and then you use these hydrogen atoms in the mechanism, which is not right. So the only nitrogen that donates atoms is going to be that nitrogen which is not close or which is not attached to the carbonyl carbon group. And for this case, it's going to be the first one. So we shall end up with the corresponding product of that format. Now this is also an hydrazine, which is 2,4-dinitrophenylhydrazine, which we use in the laboratory to confirm also for presence of both aldehydes and ketones. And this is very obvious because it's very common in organic practicals. So since majority of the work has been explained, you're going to pause the video and then you take down the examples involving what you have covered. So for this case, I use this mechanism which we discouraged earlier on simply because I just highlighted it. So for you, you may highlight it in another format. You may use another way to reach to this aldehyde simply by first converting it to an alcohol and later you partially reduce it to the aldehyde. It's as simple as that. If you can memorize this arrangement of these reagents properly, then it's very okay with you. You'll be given or awarded full marks. So others are okay because we explained everything. So that was it for this lesson. So we'll meet in the next lesson, which is going to be covering carboxylic acids together with the remaining parts. So see you in the next session. Make sure that you like the video, comment where you're having your areas of weakness, and share the video to your colleagues so that you can all benefit as a family.